This section is about maximum and minimum values. And if you think back to Calc 1, we learned about maximum and minimum values. And this value right here is a relative max, but it's not absolute max. This one is a relative min, but it's also an absolute min. There is no absolute max because the graph continues upwards infinitely. And we're doing the same idea here. Back then we used first and second derivative tests in Calc 1, and in college algebra and pre-calc we just kind of looked at it in terms of the graph. So let's look at it now in our 3D space, R3. And you can see that up here we have an absolute maximum. Let me find something to write with. Up here we have an absolute maximum. And down here we have a absolute minimum, which is also relative min. Here we have a local min, and here we have a local max. So as we look at the surfaces, we still have absolute and relative local mins and maxes, and we still call them critical points. And we're still going to look at first and second derivative tests. So I would say all the time that if you've learned Calc 1 and Calc 2, Calc 3 is not hard. And if you didn't, there's a lot of learning to go along the way. But let's start with a definition. Before we do, we say this is an absolute max because it is absolutely the maximum value for z in f of xy. So what we're looking at here is z equals f of xy. So we're saying that it is the highest z power in that area, the highest z value. And this one, if you look in that local area, it is the lowest. It is the lowest z value, but it's also the maximum z, the absolute smallest z value. And here we have a local minimum because in that area, that is the smallest z value in that area. And this is the largest z value in that area. Let's go back to this one. This is the largest z value in that area, but it's also the largest z value on the graph. So we have these values, we call them critical points, and we're going to determine if they are maximums and minimums. Okay, critical points have not changed since Calc 1. So this theorem says if f has a local maximum or minimum at a, b, and the first order partial derivatives exist there, then your partial derivative with respect to x equals 0 and your partial derivative with respect to y equals 0. Now notice that that means that we could say that the gradient of f is equal to the 0 vector, which is 0, 0. So the gradient of f, let's be specific and say the gradient of f at the point AB is equal to the 0 vector, which is the point 0, the vector 0, 0. Now, in that case, the point AB is called the critical point. And the critical point is where we determine from there if it's a maximum or a minimum. And we're going to go straight to the second derivative test. Before we do that, let's do an example. And it says, let f of xy be equal to x squared plus y squared minus 2x minus 6y plus 14. So the question is to find the critical points. We haven't done anything else outside of here, so I don't know that any of your homework simply says find the critical points. It's going to continue on from there, but the basis of this lesson is to find the critical points. So the directions say find the critical points, and then determine if they're the highest or the lowest, the maximum or the minimum. But there is one problem that starts off with find the critical points. But in order to determine if it's maximum or minimum, you have to find the critical points. I'm going to abbreviate it CP. So let's look at this problem. We're going to find our partial derivative with respect to x to be 2x minus 2. We set that equal to 0, so x equals 1. And then our partial derivative with respect to y to be 2y minus 6. Set that equal to 0, so y equals 3. So we can plug that into our original equation, and we get that z equals f of xy. And we're going to plug those in. So we say 1 plus 9 minus 2 minus 18 plus 14. So 1 plus 9 is 10, minus 2 is 8, negative 10 plus 4 is 4. So this means our critical point is at 1, 3, 4. And this equation is an elliptical paraboloid. And this is the vertex for our elliptical paraboloid. And that's the easy way to find it. This is our critical point. And from there, we could determine if it's a maximum or a minimum. There's a lot of ways to do it, but this elliptical paraboloid is positive, opening up. So it has to be an absolute minimum based upon the mathematics that we know. Based on figure 2, you can see this to be true. So let's revisit this theorem real quick. It says if f has a local maximum or minimum, then you're going to set your partial derivatives equal to 0 to find those critical points where the maximums or minimums occur. When it says find the extreme values, it's asking for us to find the critical points. So let's start with the partial derivative with respect to x, and we get negative 2x. So if we set this equal to 0, x equals 0. And our partial derivative with respect to y is 2y. So if we set this equal to 0, we get y equals 0. So we can plug that in and say z equals f of xy, which is equal to 0, 0. Our critical point tends to be 0, 0. If you want to look at it on the original plane, that's when we find the z value. So if I plug that in, I get 0 minus 0 equals 0. So our critical point is at 0, 0, 0 on the xyz plane. This is our critical point. Now here's the problem. If we look at this graph, this is neither a maximum nor a minimum. It's actually called a saddle point. So when we find critical points, we have three options. It can be a maximum, it can be a minimum, or it can be a saddle point. Kind of like a saddle that a horse rides on. So if you think about in Calc 1, this has an absolute minimum. I'm going to draw on the same graph because, it is what it is. This red one would be an absolute maximum. But when we look at x to the third, this green one has a saddle point because your critical point here is at 0, 0, but it's neither a maximum nor a minimum. Now, a great real world example of this is a mountain pass. It looks very much like this saddle point over here on this graph of the hyperboloid that we saw in the last example. So you can have a maximum, you can have a minimum, you can have a saddle point. So if we're not going to draw them, we're going to use the second derivative test to help us determine if we have a maximum, a minimum, or a saddle point. So for the second derivative test, we have three cases, but let's start at the top. Suppose we have a second partial derivatives of f. I love second derivatives, second partial derivatives, and that they're continuous on a disk with the center AB. That just means we're looking at a certain area of the graph, this disk AB, kind of like I drew in the opening video. And suppose that your partial with respect to x is equal to 0. Your partial derivative with respect to y is equal to 0. So you found the critical point. AB is the critical point. Now, we're going to look at this, and we're going to look at this D. We're going to look at this D, and D at AB is the second derivative of x times second derivative of y minus f of xy squared. Now, before we go any further, you can memorize this, which you're going to need for the second derivative test, and I don't think it's that bad. Or you can think of a matrix. Here we have f of xx, and here we have f of xy, and then f of yx and f of yy. Remember that most of the time yx is equal to xy, so let's call this xy. Now, if you find the determinant, then you have f of xx, f of yy, minus f of xy quantity squared. And that's what d is. D is equal to this value. Now, there are three cases. Case number one, case A. If d is positive, remember on a second derivative test, if it's positive, it's opening up, so you have a minimum. So if d is positive and your second derivative with respect to x is positive, then you have a local minimum. If d is positive and your second derivative is negative, that means it's opening down. We have a local maximum. So we have opening up for a minimum, opening down for a maximum. And your third case is if d is less than 0, then you have a saddle point. You do not have a maximum or a minimum. So those are your three cases. If d is positive, I would cut this down into two cases. And I would say case one, if d is positive, then you have two cases under here. If your partial derivative with your second partial derivative with respect to x is positive, then you have a local minimum. If your second derivative with respect to x is negative, then you have a local maximum. And I always think about if it's positive, you have a parabola opening up, so you have a minimum. If it's negative, you have a parabola opening down, so it's maximum. Your second case is if d is negative, then you have a saddle point. So you need this information. It's important. It's going to help you complete the rest of the lesson and the applications. So let's look at one of these. Your third case, which is not stated here, let's throw it here on the side. Your third case is what happens if d equals 0. If d equals 0, then your second derivative is not helpful. You have to look at something else. Look at the graph, go back to the first derivative, just like you did before. If the second derivative test is 0, you don't have any helpful information. One more note I'd like to make here. This PDF I'm using is apparently an unrevised version, but this one actually says it is a saddle point of F. So I'm not making that up for you, just so you know it really is written in because we know it to be true. It's not a wonder or a concern. Find the local max, mins, and saddle points for this equation. So in order to do this, step number 1 is to find the critical points. So when you're looking for local max, mins, whatever, step number 1 is find your critical points. Step number 2 is your second derivative test. So step number 1, we need to find our partial derivative with respect to x. So the first partial derivative is 4x to the third. We're going to have 0 minus 4y and 0. And we're going to set this equal to 0 and solve for x. So then we have x to the third minus y equals 0 for dividing by 4. And we kind of have to stop there because we have two variables. So we hope that y gives us two variables as well. So our partial with respect to y will be 4y to the third minus 4x. We're going to set this equal to 0. So we have y to the third minus x equals 0. So let's take one of them and let's say that y equals x to the third and plug it into the second one. And then we get y to the third minus, oh, I guess y is x to the third. So we get x to the ninth minus x equals 0. So if we factor out 8, we have x to the 8th minus 1 equals 0. So this factors into x times x to the 4th minus 1, x to the 4th plus 1. So then we have x squared plus 1, x squared minus 1. We're going to keep all the pluses happening here, and x squared minus 1 factors into x minus 1, x plus 1. So then right here we have x equals 0. Here we have imaginary. Here we have x equals 1. Here we have x equals minus 1, and here we have imaginary. Now, imaginary roots are not helpful when we're working in 3D, so we're only going to look at the real solutions. So our real solutions for our critical points are 0, 1, and negative 1. And when you plug those in, the y values are 0, 1 to the third is 1, and negative 1 to the third is negative 1. So these are our critical points. It's super important that we understand how to find critical points. How did we know to keep going? That's often a really good question here, so let me back up. This is called difference of squares. X to the fourth times x to the fourth makes x to the eighth, so we have difference of squares. And here we have difference of squares, which factored further. And here we have difference of squares, which factored further. And then we finally got done. So it's not too difficult, but when you get to this point and you notice that you have two equations with two different variables, you can only solve them using substitution, elimination, or graphing, just like we learned a long time ago. A lot of math goes into this. Now we have our critical points and our first derivatives, so we need second derivatives. So I'm going to say the second derivative with respect to x here would be 12x squared. And the second derivative with respect to y would be negative 4. Our second derivative with respect to y would be 12y squared. And our second derivative with respect to x would be negative 4. Now, most of the problems you're doing, your second derivatives with respect to x and y are going to match. So you really only have to do this one. You don't have to do both because the formula calls for that. Now, if you're going to set up the matrix, you're going to say f of xx, f of xy, f of xy, f of yy. So our d, which is our second derivative test value, gives us f of xx, f of xy, if you did the determinant, minus f of xy quantity squared. And so you can think of that either way. So let's go ahead and say this is the formula either way, whether you memorize it or build it out of the matrix. So d is equal to f of xx is 12x squared times 12y squared minus parentheses negative 4 quantity squared. So d is 144 x squared y squared minus, and 4 squared is 16. So we're going to pause there for just a second. Now what we have here is this is our d value, and we have to check each critical point. And we have 3 critical points up here. So let's start with d of 0, 0. When we plug in 0, 0, we get 0 minus 16, which is negative 16. So d is negative, so this is a saddle point. You got to go back to those cases in the previous example, in the previous screen, and when d is negative, you have a saddle point. We also have 1, 1 and negative 1, 1. So d of 1, 1 makes 144 minus 16, which is a positive value. It doesn't even matter what it is, you just need positive or negative. So you have a positive value, 144 minus 16 is 128. Now when you do this, you need to look at your second derivative with respect to x. So that would be 12x squared, which is positive. X is 1, squared is 1, times 12 is 12, which is positive. So positive means I have opening up, which is a minimum. And that's the way I think about it, rather than memorizing what's happening. And then we have d of negative 1, 1. When we put this into d, we still have positive 128. And when we put it into f of xx, we still have positive 12. So we have a minimum here as well. So what we're saying is we have a local minimum. The way that we write this up is we have a saddle point at 0, 0. We have a saddle point at 0, 0. We have a local min at 1, 1 and negative 1, negative 1. Now we don't really know exactly what this looks like, but we have a couple pictures I'm going to bring in here and show you. This is what you need to be able to achieve. You find the critical points and then run your second derivative test. And let's look at the graphs here. This is a cool graph of the figure, and it shows you can see that at 0, 0, we have a saddle point happening in here. And over here we have the local minimums. They actually match. It looks like an absolute minimum if you're looking only at this part of it. But that's not important to us. It's just important that we have a local min, and we could figure out max absolutes, but it's not required. The contour map is also cool. So if you look at the contour map here at the point, let me draw it in pink. Here at the point 1, 1, you can see that we're at a minimum because the z value is negative 0.5. And here at the point positive 1, 1, we're in the same circle, so we still have the same z value of negative 0.5. So those are local minimums. And then here at 0, 0, you can see that we have a z value of positive 1. So it kind of saddles because it's neither a maximum. It looks like it's going up, but it's the saddle point happening in the center of it all. You're given a contour map, I think, in one of your homework problems and asked to verify. So that's interesting. It's cool to look at the contour map to go with it. We're supposed to find and classify the critical points of the function and find the highest point on the graph of f. So let's start with our critical points. And we're going to take the first derivative with respect to x to be 20xy minus 10x. That would be 0. And then minus 4x to the third. and the last one is 0. So if we set this equal to 0, first of all, we should move it over because we're going to run out of space. It's longer than I expected it to be. We could factor out 2x. So we're going to say that this is 2x parentheses 10y minus 5 minus 2x squared equals 0. Now, when you look at that right off the bat, this tells us that x equals 0 from the 2x, and 10y minus 5 minus 2x squared equals 0. Now let's go look at what we have for our partial with respect to y. So the derivative of the first term is 10x squared, and the derivative of y is 1. The derivative of the next term is 0, and then we have minus 8y, and then we have 0, and then we have minus 8y to the third. So if we set this equal to 0, the only thing we can factor out here is a 2. There's not even a matching variable all the way across. So we have 5x squared minus 4y to the third equals 0. So we can say 5x squared minus 4y to the third equals 0. Now let's start with this x equals 0, and let's plug that into that equation. So we end up with 0 minus 4y to the third equals 0. So I'm going to factor out a negative 4y and have 1 plus y squared equals 0. Now this one is imaginary because 1 plus y squared, if you move the 1 to the other side, you have y squared equals negative 1. And that's an imaginary answer. So we only look at the real ones. So we have negative 4y equals 0, so y equals 0. So this one gives us the critical point of 0, 0. Now we're going to plug this one into that green equation. But in order to plug it in, first of all, I need it to be either y equals or x equals. Let's solve it for x squared. Since we have an x squared over here, that'll work out nicely. So let's say 10y minus 5 equals positive 2x squared. So if we divide, let's say x squared equals 5y minus 5 over 2, or 2.5 if you're a decimals person. So then we're going to plug that into the green equation, and we're going to say 5 times that is 25y minus 25 over 2 minus 4y to the third equals 0. And let's combine like terms. And so I'm going to say negative 25 over 2, 25 minus 4 is minus 21, or plus 21y, minus 4y to the third equals 0. My first response is, what a terrible polynomial. So let's say 0 equals, I'm going to move everything to the other side, 4y to the third minus 21y plus 25 over 2. Now, this is a very minor step in the problem. The easiest way to find the y values is to factor or quadratic formula, neither of which is going to work nicely in this case. So we're going to have to go and look at the zeros on a graphing calculator. So pause and go look at this equation on your graphing calculator. Let me take this moment to tell you that I will not do this to you on a test on purpose. So there's that. When you put it into your calculator, go ahead and say y equals and put 4x to the third minus 21x plus 25 over 2. And when you look at that graph, it'll still give you the intercepts so that you can run with it, and you can tap it and it'll tell you what the zeros are up in the top corner. I said tap on it. You probably have to hit trace. And you can see that, remember that I said y equals x. So these are technically my y values and my x values here. So it gives us our critical points. And the critical points then are the y values, in this case, y equals negative 2.55, positive 0.65, and positive 1.89, which rounds up to 1.90. So those are our 3 critical points for the y values. And then because we used x squared, we're going to have to continue on from there. And I have to go back up here. So you're going to plug each of those in here to find the x squared values, and I'm going to write them. So x squared equals 5y minus 5 over 2, so x equals plus or minus the square root of 5y minus 5 over 2. Now when you plug in this first y value of negative 2.55, you have imaginary answers, so we're going to throw that out. So when y equals 0.65, we find that x equals plus and minus 0.86. And when y equals 1.90, we find that x equals plus or minus 2.64. Pause and check that. Pause and work that out. So I have three critical values here. There's a whole lot going on. I have three critical points. The first one is 0, 0. The second one is plus or minus 0.86, comma 0.65. And the third set, technically we have five critical points, 2.64, comma 1.90. So let's look at D, and then we'll come back to these. So D is equal to f of xx, f of yy, minus f of xy quantity squared. Now we need to go back up because I don't remember f of xx. So f of x is this. Oh, that's going to be interesting. We should pick this up on a different screen. That's okay. F of x equaled, I have it written down over here, 20xy minus 10x minus 4x to the third. And f of y is equal to 10x squared minus 8y minus 8y to the third. So our second derivative with respect to x would be 20y minus 10 minus 12x squared. And then this second partial derivative with respect to y would be 20x because the derivative of y is 1 minus 0 minus 0 because we're taking the derivative with respect to y. Now our second derivative over here with respect to y would be 0 minus 8 minus 24y squared. All right, so let's talk about D. That's a mess. So we have 20y f of xx, f of yy, 20y minus 10 minus 12x squared. And the partial derivative with the second partial derivative with respect to y would be negative 8 minus 24y squared minus, and here we have 20x quantity squared. When we plug in 0, 0, let's start with that critical point. It's the easy one. We get negative 10 in the first parentheses and negative 8 in the second parentheses minus 0 squared gives us positive 80. Well, we have positive 80 for D, and our f of xx is equal to negative 10. It's opening down, so here we have a maximum at 0, 0. I don't want to rewrite them all at the end. I know, slacker. So let's talk about 0.86 and 0.65. We have plus and minus 0.86 and 0.65. We should stick a 0 on there. Now, when we plug this in, I am not going to do all the work. I'm just going to plug it on my calculator. And I find D to be negative 187.64, which is negative, which means we have a saddle point at both of them. Since it doesn't matter, hold on a second, let me finish writing. So we have a saddle point at both of them. Since this value here is positive and this value here is positive for x, it doesn't matter if you're putting in positive or negative, you can have the same value. So the next one is plus or minus 2.64, comma 1.90. And when we plug that in for D, we get 2488.72. And then our second derivative at x is negative 55.93, which is negative, so it's opening down. So we have a max at plus or minus 2.64, 1.90. Now we have maximums, but if we go back to the problem way up here, it says what is the highest point on the graph of f? So where does this most maximum point occur? Now we don't have a graph to help us come up with that. So what you want to do is you need to evaluate the z. So we're going to go back to the value of f, and we're going to say f of x equals, I'm going to switch colors, so I'm going to switch thoughts. So f of x, y equals, I'm going to call this z so I don't have to write f of x, y over and over. We have 10x squared y minus 5x squared minus 4y squared minus x to the fourth minus 2y to the fourth. Now, since all my powers of x are even, I don't have to split out the plus and minus 2.64. So we're going to say at f of 0, 0, we have 0, 0, 0, 0, 0. So this value is 0. And then at 2.64, comma 1.90, whether we're looking at positive or negative, we get the same value because it is the x's are squared here and here, and then we have x to the fourth. So the sign doesn't matter, and the value of f on that point is 8.50. We should probably check the third one just to be sure. I'm pretty sure it's not because we have maximums and that's a saddle point, but 0.86, 0.65. When we plug those in, again, I'm only going to do one of them. We have negative 1.48. Pretty sure your saddle point will not be your maximums. So this right here are the maximum, the highest points. Highest points on this graph are at, we don't have to just say it's at. There's two ways to say it. You can say, first of all, it's at x equals plus or minus 2.64, or you can say it's at plus or minus 2.64, comma 1.90, comma 8.5 or 8.50. The last one's when they're going to look for, because if we go back to the directions, it says what is the highest point on the graph. So we're looking for that point with all three values on it. Hopefully that makes sense. Some people, when they're doing the second derivative test, you'll see the box that looks like this when they're asked for highest point, and then they kind of fill it in along the way. But I don't want to find the z values unless I have to. If I only had one maximum, it is going to be my absolute maximum. So I could stop there so I don't feel the need to do a table accordingly. But this answers all of the questions that we had. And let's look at the graph of this real quick because it's given to us. Here we have the graphs from a couple different views. So you can see that we do have two matching highest points here in these two values. So that's kind of cool. You can see the saddle point happening over in here. Now, if we go back to here, notice that my leading terms, let me circle it correctly. Notice that our leading terms are both negative. So since the graph is opening down, that implies to me and to us, the graph is opening down, so we'll have maximum points. The contour graph of this is very cool as well. So on here you can see the five maximum or the 5 critical points happening. And you can read the contour map that this value here is at 7 and the other one's going to be the same. So they are the maximums. And then you can see the other critical points happening. Let's look at an example of this. When a new product is being developed, often the packaging is important in what you're doing. So a rectangular box without a lid is to be made from 12 meters squared of cardboard to make the box. Find the maximum volume of such a box. So think first of all about the fact that you're going to have a box and we can draw it out. 3D drawing isn't too bad. Hopefully you're getting better at it. Mine's a little wonky here. It's okay. You have the right idea, right? So here we have x, y, z. It doesn't really matter as long as you label it and follow it accordingly. So we're going to let the length, width, and height be x, y, and z. And remember that the volume then is x, y, z. So now that we've had that, you're making the box without a lid. So if you have 12 meters squared of cardboard, that is the surface area. So let's make a note here that the surface area is 2 times um, all of the faces. So the first face is this face here, which is xz. So 2xz plus 2yz, that's the front face. It's the front and the back, that's why it's 2, plus xy. There's only one of those because there's no lid. So the base is xy, but there's no lid, so it's just one of those. And we know that this value has to equal to 12. So we could leave the surface area part off of the formula. That would be important, but that's how we got it, is because we're looking at the surface area. So the problem is when we look at partial derivatives and what we're looking at, we do better with two variables. So let's take and solve this equation. Let's solve the second equation for z. So we're going to say 2xz. Let's factor the z out. And let's say that z times 2x plus 2y is equal to 12 minus xy. So z equals 12 minus xy over 2x plus 2y. We can put that into our volume and say x times y times that mess. Yes, it's a mess. You agree, I'm sure. Now remember, you can't cancel anything because there's pluses and minuses going on. And we can distribute, so then our volume is equal to, the top is 12xy minus x squared y squared over 2x plus 2y. So that's our volume, and it's nice. So now let's find our partial with respect to x and y. Remember that we're supposed to find the maximum volume. So that means we want to find our second derivative. Do the second derivative test and show it's a maximum, but the critical point, let's start with volume equals. Now when we take the derivative here, we're going to have to use quotient rule or chain rule. Let's use quotient rule because it's a mess. So we have the bottom, which is 2x plus 2y, times the derivative of the top, which is 12. The derivative of 12xy with respect to x is just 12y, minus the derivative here would be 2xy squared, minus the top, which is 12xy minus x squared y squared, times the derivative of the bottom, which is, with respect to x, is just 2, all over 2x plus 2y quantity squared. So our partial with respect to x, these don't match in any way. So we're going to FOIL, distribute, and all that fun stuff. So let's FOIL the front, and we get 24xy minus 4x squared y squared plus 24y squared minus 4xy to the third minus, pay attention to the sign here, it's going to have to change. So we have 24xy plus 2x squared y squared all over 2x plus 2y quantity squared. So then v of x equals, now these two are going to cancel. I'm going to start with the 24y squared in the middle minus 4xy to the third in the middle. And then these are like terms, this one and this one. So we have minus 2x squared y squared over 2x plus 2y quantity squared. Now we always know that if we can factor and make it prettier, it's going to make our life easier. So let's go ahead. I see a y squared all the way across. So let's say that v of x is equal to, let's factor out a y squared. And we have 24 minus 4xy minus 2x squared over 2x plus 2y quantity squared. So that's v sub x. Yay! Now we need to set it equal to 0 to find our critical point. Good news. If you cross multiply, if you put 0 over 1 and cross multiply, you get the numerator. So we're going to say y squared times 24 minus 4xy minus 2x squared equals 0. So y squared equals 0, so y equals 0. Now that's not helpful because that would give us a volume of 0, and that is not a maximum volume. That is not a minimum volume either. That is not a box. So let's take the other one. We have 24 minus 4xy minus 2x squared equals 0. And we're going to need that when we solve y to find our critical points moving forward. Before we leave it, let's divide by 2 and make it 12 minus 2xy minus x squared equals 0. All right, now let's find our partial derivative with respect to y. I'm going to work on the sides so that maybe they'll run parallel and we can pick up from there. So let's say v sub y is equal to, now remember this is our v back here. So our partial derivative with respect to y, I would like to rewrite it over here. V equals 12xy minus x squared y squared over 2x plus 2y. The first time, I'll be honest, the first time I did this partial derivative with respect to x, I did it wrong. So if you live in that boat, it happens. We have the bottom, which is 2x plus 2y, quotient rule, times the derivative of the top with respect to y. So we have 12x minus our derivative with respect to y will be 2y. So we have 2x squared y minus the top, which is 12xy minus x squared y squared, times the derivative of the bottom with respect to y is just 2, all over 2x plus 2y quantity squared. So now we're going to do FOIL and distribute and combine like terms. So we have 24x squared minus 4x to the third y plus 24xy minus 4x squared y squared minus, now don't forget this when we distribute, 24xy plus 2x squared y squared. You can see these 24xy's canceled again. That's nice. And we have 2x plus 2y quantity squared. So we're going to say v sub y is equal to, it's not quite that long. Let's draw that line again. I'm going to keep the 24x squared minus 4x to the third y. And then you can see that these two are like terms again. They're very similar to what we ended up with last time. Minus 2x squared y squared over 2x plus 2y quantity squared. So our first derivative with respect to y, we can factor out an x squared on the top. And we have 24 minus 4xy minus 2y squared over 2x plus 2y quantity squared. Now, in order to find our critical point, we're going to set this equal to 0. And again, if we cross multiply, we end up with the numerator, minus 4xy minus 2y squared equals 0. So then x squared equals 0. Again, this gives you x equals 0, which is a volume of 0. Not helpful. So we have 24 minus 4xy minus 2y squared equals 0. Let's go ahead and divide by 2. So we have 12 minus 2xy minus y squared equals 0. Now, if you look at these are two very similar equations, and there's a lot of ways that we can do this, but substitution, you could solve for x, y, and sub it into the other one. But notice how similar these equations are. Let's bring them over. So we have 12 minus 2xy minus x squared equals 0, and 12 minus 2xy minus y squared equals 0. So if we do elimination here and subtract, we end up with negative x squared plus y squared equals 0. So we end up with x squared equals y squared. Now that's going to tell us right there that they have to be non-negative, and they their squared values have to match. So we literally could say x equals y because you can't have a negative side length on the box. We could plug this into either of these equations. It does not matter. Let's run over here and put it in x. So we're going to say 12 minus 2xy minus x squared equals 0. Let's plug a y in for it. So 12 minus 2y squared minus y squared equals 0. So let's move the 12 to the other side. We have negative 3y squared equals negative 12. Y squared equals positive 4. So y equals plus and minus 2. But remember, you can't have a negative value. So y equals 2, which tells us that x equals 2. Based on up here, x has to equal y. Since x equals y, then we can go back up to the top of the problem up here and find z. So x and y both equal 2. So we're going to say 12 minus 2 times 2 is 4 over 4 plus 4, which is 8. So 8 over 8 is 1. So our z value is 1. So our critical point is the point 2, 2, 1. Now we only have that, so it should be a maximum, and we're going to hope and pray that it is. This is a maximum, and we could plug it into the volume. The volume, remember, is xyz. So the volume is 2 times 2 times 1, which is 4 meters cubed. It is a maximum. You could run the second derivative test, but do you really want to go do the second derivative of this? Based on the fact that you can't have any negatives because it is the sides of a box, this has to be your maximum. So this has to be your maximum volume. And I agree and completely say to run with it that way. Now, there's one more thing we need to talk about before we wrap up this section, and it is absolute maximums and minimums values. Absolute maximums and minimum values. Now, as we learned in lower mathematics and in Calc 1 and etc., in this graph we have a minimum here and a maximum here. And at this point, x equals to some number like 3, we have an absolute maximum because it's absolutely the highest point on the graph. And that translates the same into our vectors and our surfaces in 3D spaces. But if we have a closed interval, let's say we have it closed like this, no matter how you draw your closed interval, there will be an absolute min and there will be an absolute max. And it might be at the endpoints, but it might not. In this case, they're the endpoints. Here we have a relative min, here we have a relative max. But let's say we drew it like this. Here we have an absolute max, which happens to be an endpoint. Often they are, and this would be our absolute min. Now we still have a local max here, a local min, and another local max. So we have a max, and a min. And we did increasing and decreasing and all that fun stuff. Now what's important to note is that if you have a closed graph, then you're going to have absolute values. That's what we're going to find right here. So let's look at this definition. This didn't work in the PDF I have access to, so this is actually from your e-text on WebAssign. So it says if AB is a point in the domain of two variables, then f of AB is the absolute max if it's higher than all the other z values for your function f of xy in the domain. And it's an absolute min if it's lower than all of your values in the domain. And we've got that, but let's talk about what bounded means real quick. Bounded set in R2 is one that's contained in some disk. In other words, it's finite in extent. So the terms closed and bounded sets, you can look at this extreme theorem here. This is what I want you to see is this extreme theorem. It says that if f is continuous on a closed bounded set in R2, that means it's closed, kind of like these last two examples. It's closed, it stops. It's not got any, it's not infinite in any direction. So it's a closed bounded set. That's really what bounded is. So closed means the endpoints are included, and bounded means it's got a start and an end. Then f attains some absolute maximum value and an absolute minimum value at some points. So if you have a closed, that means your endpoints are included, and bounded, that means it can't go to infinity. It has to start and stop at finite values. Then you will have an absolute maximum and you will have an absolute minimum. And you can see that from these two pictures that I drew. Not this one. This one has, it's not bounded. These two are closed and they are bounded. Now let's put this one in green and say this one is not closed, but it is bounded. Because it is not closed, you don't have an absolute minimum because the point is not included. So it is important that it is closed. It is closed, that means the endpoints are included, and it is bounded. So let's talk about closed real quick. These are some cute examples. The top two are closed. That means that you have boundaries and they're all included. And in the bottom one, it kind of makes sense. An open circle, a dotted line means not closed, not included. And even if you only have one dot, even if you only have one dot that's not included here, then it still is not closed. So let's go back to here. These two pink ones right here are closed and bounded, and this green one is not closed because the endpoint is not included. So it's important to note that if you have a closed bounded set in R2, then you will have an absolute maximum and an absolute minimum. So let's put this into how is it helpful for you. So to find the absolute maximum and minimum values on a closed bounded set. So if you have a closed bounded set, you have endpoints and it's closed and it's bounded. You have endpoints and they're included. That's what closed and bounded means. So number one, find your critical points and find the values of f. So that means find the z points. So find z equals for your critical points. Number two, find the extreme values on the boundaries. So find z equals at the endpoints. And then number three, the largest values from these are your absolute maximum, and the smallest is your absolute minimum, and that makes sense. So your largest z will be your absolute max, and your smallest z will be your absolute min. So let's look at one of these. So this problem says find the absolute max and min values of the function on the rectangle given. Now notice you're given intervals for x and intervals for y that are including both endpoints. So it is bounded because we have intervals, and it is closed because the endpoints are included. So you will have an absolute max and an absolute min. So let's start with the partial derivative with respect to x. So the partial derivative with respect to x is 2x minus 2y, and then 0. And we set this equal to 0, and we find that x equals y. Now our partial derivative with respect to y, let's do it over here. Our partial derivative with respect to y is going to be negative 2x plus 2 equals 0. So then we find negative 2x equals negative 2, so x equals 1. Looking at this first one, x equals y, two variables needs two equations. We could back this up and say x minus y equals 0, x equals y. So since x equals 1, then y equals 1. So our only critical point is at 1, 1. Wasn't that nice of them? So we need to find our second derivative with respect to x to be 2, and our second derivative with respect to y. Let's label our critical point real quick. Sorry about the delay there. So our second derivative with respect to y is 0. Interesting fact. And then our second derivative with respect to y is 0. So our second derivative test may not be helpful. There's way too many zeros going on here. I would like to look at the second derivative test. So it says these two minus this one squared. So we have 2 times 0 minus 0 squared is 0. So it's not helpful, of course. All right, so if you think about what we're doing, we have a critical point at 1, 1. So we're going to say f of xy equals x squared minus 2xy plus 2y. This is our given equation, and we have x is between 0 and 3, and y is between 0 and 2. And we have a critical point of 1, 1. Let's write over here. Our critical point is 1, 1. So the question is, because we have a closed bounded graph, we know that we have an absolute minimum and an absolute maximum. Now you can't just say 0, 0, and 3, 2, because that's not necessarily true. So we're going to start with f of, let's look at x being 0 with any y, in which case our equation becomes 0 minus 0 plus 2y. Now we know that y is between 0 and 2. So this means that when we plug in 0, if we have f of 0, 0, we get 0, and f of 0, 2, we get 4. So here we have the point 0, 0, 0, and here we have the point 0, 2, 4. And then let's look at our second x value of 3, and we have any y. So if we plug in 3 for x, we have 9 minus 6y plus 2y. 3 times 2 is 6, yeah. So this gives me 9 minus 4y. So again, we're going to plug in our maximum and minimum values for y. Our minimum value is 0. So that's going to give us 9 minus 0 is 9. So we have the point 0. Nope, nope, the x value is 3. So we have the point 3, 0, 9. Now it's already higher than this one, so we could throw that one out. So let's say that we have 3 and our maximum y value is 2. So when we plug this in, we have 9 minus 8 is 1. So we have the point 3, 2, 1. The y value is 1, which is between 0 and 9. So we can throw that one out. Now we need to try the x values. We started with the x, now we need to do the y. So let's let x be any value and y is 0. So we're going to go back up to this original equation. And when we plug in 0 for y, we have x squared, and the rest of it goes away. And our our x bounds are between 0 and 3. So when y equals 0, we're going to first of all let x equals 0, which is 0. So we have the point 0, 0, 0, which corresponds to the one up above. So it looks like 0, 0, 0 might be a minimum. And when y equals 0, x also equals 3, which is 9. So we have the point 3, 0, 9. Are they always going to match? Not necessarily. So don't bank on that. And then we're going to say when x equals 0, y could equal 2. So we need to go back to the original f of x up here. And when we plug in 2 for y, we keep x squared minus 2 times 2 is 4x plus 4. So now we're going to say when y is 2, x can be 0 and x can be 3. I'm going to help myself out there. So I'm going to plug in 0 for x. And when we do that, we get 4 here, which gives us the point 0, 2, 4. And when we plug in 3 and 2, we get 9 minus 12 is negative 3, plus 4 is 1. So we have the point 3, 2, 1. This y value is in between, and the y value of 4 is in between, so that's not helpful. Now we need to look at our critical point of 1, 1. Right here, we've checked we've checked both of the endpoints for x, and here we've checked both of the endpoints for y. So now our last value is our critical point 1, 1. And we're going to go back to the original equation. And when we plug in 1, we get 1 squared is 1, minus 2 plus 2, which is 1. So this gives us the point 1, 1, 1. Notice this y value is between 0 and 9. So our minimum point is 0, 0, 0, and our maximum point is 3, 0, 9. So what we say is we have a minimum, we have an absolute minimum at, the notation used here is f of 0, 0, which is equal to 0. And we have an absolute maximum at f of 3, 0, which is equal to 9, which is true in both of these cases. If you go back and look at them, I think this is a highlighter and it might work. So here both of these are f of 3, 0, and here both of these are f of 0, 0. And our critical point didn't come into play at all, but that's not necessarily true. It's it's quite a bit of work. It's not overly hard. It's just a little tedious, but I think that you can do it pretty easily. And I didn't give you very many of these, so I hope that you'll figure it out and enjoy this lesson. Have a great day.